In this problem, we are given a directed graph with such a property that for any pair of vertices, let's say 0 and 17, there is a path from 0 to 17 and from 17 to 0, and this is true for any pair of vertices. This implies that if we start running DFS on any node of this graph, then we will visit every node in this graph. If we run DFS visit on that node, we will visit every node in the graph. So let's assume that we're going to run DFS visit on node 0. How will we calculate the length of the longest cycle in the graph? Well, the idea is that as DFS visit runs, whenever a node encounters the source, the node from which we started DFS visit, whenever there is an edge that finds gray node, when we verify that this gray node is indeed our source, that means that we reached the end of the cycle that starts with 0 and that ends with 0. At this point, we need to reset distance of this node. And it has to be done very carefully, but if distance of this node is -1, remember that we set all the distances to -1 for this purpose because we are looking for the maximum length of the cycle. And therefore, we're setting it to the smallest length possible, which is -1. So when we start running DFS visit from 0, we reach 11, let's say, reach by some path 11, and then when we look at the adjacency list of 11 and find 0, we also find that this edge, 11, 0, corresponds to the gray node 0, and also this 0, not just a gray node, but it is also the source from which we started running DFS visit. That means that there is exactly one edge between 11 to 0. So we set distance of 11 to, if this distance of 11 is -1 at this point, then we set it to 1. So we found a path from 11 to 0 of one edge. And as we return recursive calls, as we back up, trace back the path from 11 back to 0, we update distances on each node. How do we update these distances? For example, on node 14, we have a couple of neighbors, right? So each time we return from a neighbor, we update distance of this node 14. Each time we return from for example, we can return from 4 and we update distance of 14. Then when we return from 8, we update distance from of 14 to the maximum. We set it to the maximum. So there might be several paths from 14 to 0. For example, path consisting only of 2 nodes, of 2 edges. 14, 15, 0. This path consists of 2 edges. So when we encountered 0 from 15, it is 1 edge. When we back up to 14, it is 2 edges. At this point, we compare the distance that is at 14, whatever is stored there. If this distance returned from 15, distance of 15 is 1 plus 1 more, is it greater than what is stored as distance of 14? If it is greater, then we reset distance of 14 to that number. And as we return to 0, we will calculate correct distances. So at the end of this procedure, distance at 0 will have the total number of edges on the longest cycle to which 0 belongs. And let's just run this example using this graph, and with two small things that we need to keep in mind. In the adjacency of 7, 0, in the adjacency of 7, 0 comes before 9. In the adjacency of 5, we have node 6 that comes before 0. Only these things that we need to remember, because these conditions are important and we'll see why. Now, let's start at 0. Initially, distance at 0, initially we set distances of every node to -1. And the rest of the nodes, let's assume that adjacency lists of the rest of the nodes are stored in increasing order of vertices. So we start at 0, we go to 1, 2, 3, 4, 5. 5 has 6 before 0, so it goes to 6, and then it goes to 7, and here we go to 0 first. So when from 7 we encountered 0, we check, okay, 0 is gray, is it the source? Yes, it is the source. How can we check it? Well, its discovery time is equal to 1, and it is true only for the source node. Aha, it is the source node, so we're going to set distance of 7 to 1. And now we're going to proceed. We return, we back up our recursion, we back up to 6. And 6 sees that we returned from 7. Distance of 7 is 1. That means distance of 6 will be 1 plus 1 will be 2. Is it greater than -1? Yes, it is greater than -1. So we set distance to distance from 6 to 2. Again, what does this distance mean? It means there is a path of 2 edges from 6 to 0. Then we return to 5, to node 5. Node 5 has checks its distance of the return child. Return child has distance 2 plus 1, that would be 3. Right now distance of 5 is -1, 3 is greater than -1, so we set distance of 5 to 3. And after that, 5 visits 0. 0 is gray, and also it is the source. At this point, we need to be careful. We do not want to reset distance of 5 to 1, because our distance that is currently of 5 is 3. So we need to check, aha, we met gray vertex, which is the source. Is our distance greater than -1? Yes, so we do not want to reset this distance from 5 to 0 to 1, because we already have a longer path to get from 5 to 0, which consists of 3 edges. So we do not update distance of 5, and we return to 4. We are at 4 right now, and 4 has another child, 6. It checks first, it returns from 5 to 4, and it resets its distance. Is 3 plus 1 equal to 4 greater than -1? Yes, so we set this distance to 4, and then we look at node 6. The next neighbor of 4 is 6, but it is black already. We still need to process black nodes. We do not call DFS visit on 6, but we need to take into account distance from 6 to 0 plus this edge 1, and compare it with this distance that is stored at 4 and update it to maximum. Distance from 6 to 0 is 2 plus this edge 1 would be 3. 3 is not greater than 4, so we do not update this distance of node 4. The next node that you can go from 4 is 8, and it is white, so we continue with this white node. We call DFS visit on 8, and then we call DFS visit on 9. From 9 we call DFS visit on 10. From 10 we call DFS visit on 11, and from 11 we have edge to 0. We check, aha, 0 is gray, Is it the source? Yes, it is the source. So check if distance of 11 to negative is equal to -1, then we can set the distance from 11 to 0 to 1. It means to go from 11 to 0, there is a path exists from consisting of one edge. Then we return our recursion call to 10. When this recursive call is returned to 10 checks distance calculated at 11. This is 1 plus this one edge that makes distance of 2 at 10, and then it will return to 9. 9 has only one neighbor. It checks after this call returned, it checks distance of the child. It's 2. 2 plus 1 would be 3. 3 is greater than -1, so we set distance of 9 to 3. And then it will be returned to 8. 8 doesn't have any more neighbors, so it checks distance from 9 is 3 plus this one edge is 4. Distance of node 8 is 4. And it will return to the node 4. At this point, it returned from 8. It needs to check up the distance from the returned child. 4 plus this one edge makes distance 5. So you need to update a distance of 4, of node 4 to 5. You update it. Okay, and after this we already explored every neighbor of node 4 and we return to node 3. We return to node 3, doesn't have any more neighbors, we return and we need to update distance of 3 with distance of 4 plus 1, which is 6. And then we return to 2, and 2 needs to update its distance from the distance of returned child, plus 1 would be 7. So right now distance of 2 is 7, and now it looks at the next neighbor, which is also white, so we call DFS visit on 12. From here we call it on 13, on 14. At this point, at 14, it first will explore this edge 14, 8, but 8 is already black. But we still need to take into account distances from black nodes. So we look up distance of this black node. We do not call DFS visit on 8, but we look up its distance of this node. Its distance is 4 plus this one edge. It will have 5. 5 is greater than -1, so we'll set distance of 14 to 5. And then we'll call DFS visit on the next white node, which is 15. We call DFS visit on 15. 15 checks this node, this edge, the only edge it has, to 0. It is gray and it is the source, so it sets, and its distance is -1, so it can reset this distance to 1. Means there is a path from 15 to 0 of one edge. And then this node returns the recursive call to 14, and 14 checks up, okay, distance of 15 is 1 plus this one edge is 2. Is it greater than distance, current distance stored at this node? No. So it's not greater. And then it will check actually this distance of, I actually missed this node, but at this point let's let's assume that 4 is stored after 15, right? So we explore 4 right now. It's black, but we still need to check its distance. Its distance is 5 plus this edge will make distance from 14. If you go from 14 to 0 through this node 4, that will make distance of this path to 6. So we need to update distance of 14 to 6 here. After that we explored every edge of 14, and we can back up to 13. 13 looks at the distance of the calculated child. It's 6. 6 plus this edge 1 is 7, and it backs up to 12. 12 updates its distance with the returned child's distance. 7 plus 1 would be 8. 8 is greater than -1, so it sets its distance to 8, and it calls DFS visit on the next white neighbor. Next white neighbor is 16. This calls on 14. This will look at this black neighbor and updates its distance from the black neighbor. 6 plus 1 would be 7, so it updates distance of 17 to 7. And then it looks at the next black child, and black child 15 has distance of 1. 1 plus 1 is 2, it's not greater than 7. So we are done processing all the neighbors of node 17. We return to 16. 16 looks at the return child's distance. It's 7 plus 1 is 8, so it updates its distance to 8 and returns to 12. 12 looks at the distance of the return neighbor. It's 8 plus 1 is 9, greater than its current stored value, so it updates its distance to 9. And after that it will return call to 2. 2 checks the distance of the returned child. It's 9 plus 1 is 10, is greater than 7, so we're going to update this value to 10. And after that it will return call to 1, and 1 will look at the distance of this return the neighbor, and 10 plus 1 will be 11. It sets its distance to 11. It will return it to 0. 0 has only explored 1, so it will update its distance to 11 plus 1 would be 12, and then it will check the black child 3. 6 plus 1 would be 7, not greater than 12. Okay, and it doesn't have any more edges, and at this point all the distances of all nodes are set, and at this point distance of 0 holds number 12. Now, and this would be the longest cycle that starts at 0 and ends at 0. Now we need to think, how can we actually traverse this longest cycle? What other information do we need to maintain at each node? So what we need to maintain is we're going to use parents array, but instead of parents in this array, we're going to store parents at I. We will stores a child or a neighbor, not necessarily child, a neighbor whose distance is maximum. Distance is maximum. And in this way, by traversing parents array, we can traverse where do we come from. So for example, we came to 0, we started 0, child that has longest path to 0 will be 1. So parents of 0 will store 1. Parents of 1 will store 2. Parents of 2 will store 12. Parents of 12 will store 8. So we basically traversing this cycle. Let me highlight this cycle with a different color. So we have this longest cycle that we follow by update. As we update distance, we also update parents array. If we update distance to the max length, then we update parents at I to the child that had that max distance. Okay, so this is our longest path that we found that contains exactly 12 edges. So we got here from 5, got here from this, this, and this, and this. This would be our longest cycle that contains 12 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is what we do as our first step. Unfortunately, there are more things that we need to consider, and I will explain you why. But first of all, let's summarize our outline of algorithm. What did we do? We maintained two arrays, parents and distance, and there are really three choices for each vertex neighbor. Neighbor can be white, then you call DFS visit on that white neighbor, and after DFS visit returns, only after that you update distance of the current node with the distance of this child plus 1 if it will be maximum. Second, node can be gray. Your neighbor of the current node can be gray. You only consider gray nodes that are the source. Only source is considered in this case. And you only update distances if your current distance is -1. If distance is -1, then, and it is the source, then you set your distance to 1. So those are two cases. And the third case, let me put the third case here. So the third case is when a neighbor is black. So if the neighbor is black, then what do? You still need to check the distance of that black node. Check distance of black neighbor, and if distance of black neighbor plus 1 is greater than your current max, than your distance of the current node, then you need to reset distance of the current node to distance plus 1 of the black neighbor. And this is the whole outline of the algorithm with all conditions that you need to consider, and this would be correct to find the longest cycle to which the node on which we ran belongs. We can find it, but let's consider another case, which is case of this graph. Let's consider the case of this graph. If we choose to run on 0 our algorithm, we run on 0, we go to 1, go to 2, go to go to 3, go to 4, go to 5, go to 6, go to 7, we encountered the gray node 2 right now. Because it is 2, not the source, we do not update the distance here to the distance of 2 minus 1. In fact, distance of 2 right now is also -1. So because 2 is not the source, we do not update this distance coming back from this child. Because 2 was gray and it is not the source, so we do not update distance of this node coming from this gray node. And that means that distance of 7, as it was -1, it remains -1. Now we're backing up to 6. We're coming from 6. Here we need to check if distance of 7 is not -1. Only then we update distance of 6 as distance of 7 plus 1. So, but this is -1, so we do not reset distance of 6. So we're coming back to 5, and a distance of 6 is -1, so we do not update distance of 5, it is still -1. Distance of 5 -1, so we do not update distance of 4 as distance of 5 plus 1, it is still -1. And so this distance is also -1. What it means is that what these -1s mean is that you cannot reach from these nodes, node 0, through simple path that doesn't repeat any node. What it means is that we had a path 0, 1, 2, gray node. And to go from any of these nodes back to 0, you have to path again through this node 2, which was already on the path. And this node cannot be, this cycle has to be simple cycle. It has to start at 0, it has to end with 0. So you cannot repeat, any other node cannot be repeated on this cycle. We're only looking at simple cycles. If we start at 0, we have to end with 0, but no other node is repeated on that cycle. So these distances show that there is no path from this node to node 0, direct path. There is only path, might be only path through some nodes that already was encountered on this cycle. So as we back up to 2, we do not update distance of 2 coming up from 3, because distance of 3 is -1. We follow with the next child. Next child is 8. From 8 to 0 we found gray node, and it is the source. And the distance of 8 is -1, so we can set it to 1. Path from 8 to 0 contains 1 edge. And then when we return from 8, distance of 8 is 1, greater than -1. So we can set up distance of 2 as 1 plus 1 is 2, greater than -1. So we set it to 2. That means there is a path from 2 to 0 out of 2 edges. And then when we back up to 1, 1 checks distance of 2 is not -1, it is 2, plus 1 is 3, is greater than -1. So we set it to 3. And then when we come back to 0, we set this distance to 4. Notice what happened here. Even though that this graph has longer cycle than just 4 edges, we only identified a cycle that has exactly 4 edges. That means that our approach, it is a good approach, but it is not a good enough approach. That means that to make this algorithm correct, we really need to apply that approach and start running DFS visit on every node in the graph. So to correct our approach, we need to implement that approach that we discussed, but we have to call that approach and run that, reset all distances, all parents, and rerun that approach on every node on the graph. And whichever node will result in the longest distance, that would be the node, the source on which we should find the longest cycle. So really you need to have a for loop that runs on all the nodes, and for each node you need to reset distance and parents and run DFS visit that updates distance and parents in the way I explained before. And you also need to maintain some temporary variable like temporary source and temporary max length of the cycle, and update this source and max with the longest distance found for each node. And then after you run on each node, you will know what is the longest cycle and what is the corresponding source that you ran it on to find this longest cycle. And after you finish with this for loop, you can run one more time on that source to retrieve that longest cycle. I hope that was helpful. And if you have any more questions, please send me an email or come to the office hours.